Welcome to the Explainer. Today, we're decoding something that is absolutely crucial if you work anywhere near industrial piping. We're talking about the ASME B16.11 standard. You know, if you're in oil, gas, chemical processing, or power generation, you've definitely run into this. But here's the thing. Really understanding what it dictates, that can literally mean the difference between a system that flows perfectly and, well, a catastrophic failure. Let's get right into it.
So, I want to start by throwing this question out there, because it's probably the biggest misconception engineers and procurement folks run into when they're sizing and buying forged fittings. Does a 3,000-pound fitting actually mean it withstands exactly 3,000 psi in all situations? The short answer? No, it doesn't. And by the end of this explainer, I'm going to show you exactly why the real answer might actually surprise you and how getting this wrong can cause some serious damage to your piping infrastructure.
Okay, here's our roadmap for today. We're going to cover 1. What is ASME B16.11? 2. Types of forged fittings. 3. Decoding the pressure classes. 4. The pipe schedule connection. And finally, 5. Why this standard matters.
Let's dive into Section 1. What is ASME B16.11? The foundation of forged fittings.
At its core, ASME B16.11 is the governing standard established by the American Society of Mechanical Engineers. It covers all the nitty-gritty details: the pressure, temperature ratings, exact dimensions, specific tolerances, markings, and material requirements for forged fittings. We're talking about those solid blocks of steel, carbon, alloy, or stainless, that get forged and then meticulously machined into incredibly precise shapes like elbows, T's, and couplings. And keep in mind, this standard specifically applies to two types of connections: socket welding and threaded fittings. I really love this quote from one of our sources because it just simplifies the whole thing beautifully. ASME B1611 is like the recipe for connection and union fittings and piping systems. Think of it as your master recipe. If you're building a high-pressure piping system, this recipe is what ensures every single union and connection component is designed with the perfect geometry and the right material so they all work together seamlessly, no matter what crazy temperature or pressure the fluid inside is throwing at them. Moving on to Section 2, Types of Forged Fittings, Exploring the Components. Now, this brilliantly illustrates the sheer level of detail this standard actually demands. Looking at the dimensional specs for socket welding fittings, notice how it doesn't just say, hey, go make an elbow. It strictly dictates the exact center to bottom of socket dimensions, the bore diameters, and the minimum socket depths. And that socket depth, that is absolutely critical, because it guarantees you get proper pipe insertion while intentionally leaving this tiny, very specific gap. You need that gap to allow for thermal expansion during the welding process. Without it, the weld could easily crack under stress. Now, contrast that with the threaded fittings. While socket welds rely on physically melting metal together, threaded fittings are all about mechanical engagement. Here, the standard says that the threaded lengths and wall thicknesses have to strictly comply with other specific standards, like NPT, the National Pipe Thread Standard. It actually enforces minimum lengths of perfect threads. Why? So that when you torque that fitting down, you get an absolutely tight, secure, and leak-proof fit every single time.
All right, Section 3. Decoding the pressure classes. 3,000 pound versus 6,000 pound.
So the standard categorizes these fittings into specific classes, and these classes dictate the wall thickness and the overall structural strength. For threaded fittings, you've got classes 2,000, 3,000, and 6,000. But notice what happens with socket weld fittings. They drop the 2,000 class completely and add a 9,000 class instead. That's because Class 2,000 is strictly for lower pressure threaded systems. On the flip side, Class 9,000 is reserved exclusively for the most extreme, highly demanding socket weld applications where you're dealing with incredibly thick pipe walls. But for most standard process piping, Class 3,000 is basically going to be your default workhorse.
I want you to remember this number, 2. Why? Because when you make the jump from a 3,000-pound fitting to a 6,000-pound fitting, you are essentially doubling its physical characteristics. A 6,000-pound fitting gives you approximately double the pressure capacity and nearly double the wall thickness of the 3,000-pound version. And because you're adding this massive amount of solid steel, it's also going to weigh almost twice as much. And yep, it's going to cost you about 1.5 to 2 times as much to procure. It is a significantly heavier, beefier piece of hardware. Let's get to Section 4, the pipe schedule connection. Matching bores. Now this is really the climax of this explainer, where we finally address that big myth I mentioned right at the start. What's really interesting here is how this completely reframes the way we think about pressure classes. See, ASME B16.11 doesn't just declare some universal maximum pressure.
Instead, it defines the pressure class based on the wall thickness of the matching pipe. Take a look at this data. A 3,000-pound fitting, whether it's threaded or socket weld, is specifically designed to match the inner diameter of a Schedule 80 pipe. Meanwhile, a 6,000-pound fitting is engineered to match a Schedule 160 pipe.
So here is the crucial takeaway. You cannot just mix and match these components and assume you're safe. If an engineer says, hey, let's just use a 6,000-pound fitting on a Schedule 80 pipe so we have extra pressure capacity, they are literally creating a massive safety hazard. When you connect mismatched classes and schedules, the inner bore of the pipe won't align perfectly with the inner bore of the fitting. That creates a physical step, basically a tiny ledge right inside the pipe. And when high-speed fluid hits that step, it causes turbulence, erosion, flow restriction, and eventually fatigue cracking. Those bores have to match perfectly, no exceptions.
Which brings us right back to our opening question. While it's a super handy rule of thumb out in the field to say, hey, 3,000 class handles 3,000 psi at ambient temperature, the true, actual maximum pressure capacity is dynamic. It shifts based on temperature, because metals naturally lose strength as they get hotter, which means you have to apply derating factors. It also depends heavily on your material grade, whether you're using carbon steel, alloy, or stainless. And of course, it depends on the fitting series, the pipe schedule, and the connection type. The point is, ASME B16.11 is a whole system of variables, not just one single static number.
Wrapping things up with Section 5. Why this standard matters. The real-world benefits. Following this strict recipe of this standard gives you 3 core advantages. First and foremost, safety and reliability. By sticking to these rules, you prevent those dangerous bore mismatches we just talked about and ensure your system won't fail under high pressure. Second is global interchangeability. Because the standard dictates exact dimensions and thread types, a procurement officer can seamlessly source a 3,000-pound socket weld elbow from a manufacturer in, say, India, and it will perfectly mate with a Schedule 80 pipe manufactured in the United States. And finally, it guarantees a strict baseline of quality and structural uniformity. That's what keeps these massive industrial sites running safely for decades.
I want to leave you with a bit of a provocative thought to take back to your own projects. Think about your current piping material specs. Are you absolutely certain that your fitting classes are perfectly matched to your pipe schedules across the board? Or could there be bore mismatches hiding in your system right now, just quietly generating turbulence and fatigue? It might be time to pull out those ASME B16.11 dimension tables and do a double check. Thanks so much for joining me for this explainer, and keep learning.